Today we're going to look at right triangle trigonometry and some of its applications. You've most likely seen a lot of this before. This is something that you do in geometry in high school, maybe a little bit in Algebra 2 or AFM or whatever they're calling it now. It's our kind of obligatory right triangle questions. It's ladders leaning against walls, trees casting shadows, those types of things. So we're moving now in our course kind of outside of the unit circle a little bit and not so much focusing on what's going on inside the circle and the graphs, but what's going on in this one particular triangle. We'll start with right triangles, and then as we go through the rest of the trig applications, we'll move outside of right triangles, right? Because not every triangle is a right triangle, although we do love right triangles. So we're going to use the trig functions to find some angles. We're going to also use the angles to find the sides, and then we'll be able to what will come to be known as solve the triangle, where it's just kind of a couple of things written on the triangle and you have to fill out the rest. And sometimes the triangles have a real life story behind them and sometimes they don't. We saw something like this earlier in the course where I have a few sides and I have a couple of angles marked, and somebody somewhere says, let this be theta. Now theta can be any part of the triangle, any angle in the triangle. If you're talking about a right triangle though, then theta will not be the right angle. So it could be here or it could be here. For this problem, we're looking at theta being here, so that means this is my adjacent side. Looking out, if you were standing on theta looking out, that's my opposite, and of course the side across from the hypotenuse, because I have my 90-degree angle marked, is my hypotenuse. We remember our best friend SOHCAHTOA and our best friend, our Pythagorean theorem, right? So if I got a right triangle, I know the sides squared, add them together, and I get my hypotenuse squared. So if I have a 3 here and something here, and my hypotenuse is 5, this is of course our 3, 4, 5 triangle. It's one of the Pythagorean triples. Eventually you start to kind of remember them, but if not, you can kind of just go through and say, well, I have my adjacent, I got to find out what the opposite is. The hypotenuse is 5. Oh, my opposite must be a 4. So I'm talking about a 3, 4, 5 triangle. I'm going to go backwards. So I could take out my question mark and put in the 4. And now all my sides are marked. So I can find the sine of this angle, this theta, even though I don't know what theta is. Whatever it is, its sine is opposite over hypotenuse. It's 4/5. Cos, 3/5. Tangent, and tangent's pretty popular for the application problems, but it doesn't have to be a tangent. You can use any trig function with the application problems that works, that makes sense. And that'd be opposite over my adjacent, so that'd be 4/3. And you can find them all. And we looked at something like this in our very beginning of the course in the first chapter. In the second chapter, we said, oh, well, if I know if the sine of theta is 4/5, I can use my handy-dandy calculator and inverse function and say what angle has the sine of 4/5 and then find out what theta is. I am going to see if I can pull up my calculator, and I'll leave it in degrees just because it's going to be a little bit easier to visualize than a irrational number for radians, and say inverse sine of 4/5, that angle's about 53 degrees. So if I say go back to my triangle, I can take this out and say, well, he's about a 53. That's about a 90. I know that my angles have to add up to 180 within the triangle. So 180 minus the 143. I kind of do it the old school way if I don't have my calculator. That has to be 37 degrees, and you have solved the triangle. Right, that's the idea. Right triangle trig says, well, you don't have everything. They're going to give you some information, like B is 4. Let me go backwards. B is 4, and this angle A is 35. They have to mark this right triangle. If it's not marked or it doesn't say, hey, this is a right triangle, you can't assume that it is, regardless of what the graph looks like. As you see through, as we go through the rest of the chapter, you kind of tend to draw triangles all the same way, so they all look the same. So you can't just look at it and say, oh, that's obviously a right triangle or an isosceles triangle or something like that. Well, I have this, so if A was my theta, I have the adjacent, so I can find A pretty easily by using tangent and say, well, the tan of a 35-degree angle, that's opposite, which I don't have, that's A over adjacent, which is a 4. And then I could use my calculator to figure out what the tangent of a 35-degree angle is, take that out, and put that weird number in. Tan of a 35 is about, I'm going to say 7002. So I'm going to take that out and have that equal to A over 4. Now, if I still have my calculator on the screen, I would just say times 4 by both sides. I wouldn't worry about retyping it and round it. I'd just leave the whole thing. So that way I got A equal to, let's see, that's an 8, that's a 0, that's a 0, that's a 28. If I can remember how to do this by hand, I think that's like a 2.8-ish. You could have also, let's round that to just a 2.8. And now I can use Pythagorean theorem to find C. Now, let's say you don't like to use tangent and you rather use cosine and say, well, the cosine of a 35-degree angle is adjacent, which is 4, over the hypotenuse of C. And then you would find C and then use Pythagorean theorem to find A. Either way is fine. It's just about what you see. As you go through these problems, if you have to do multiple steps, go back to the given because there's no rounding error in the given. So for this one, we didn't need to go back and use this angle again. But if you had to pick an angle to use, don't pick this angle that's rounded. Pick this angle that was given as a hard number, because as you round, that rounding error compounds. That's for A and C, and we can find the rest of it because we know that this is 2.8. This was a 4. Oh, I didn't solve that one, but we can solve for C a couple of different ways. I know that's a 35, so B, I'm going to do it the lazy way. I got two angles. That's a 125. I know this has to add up to 180, right? So this has to be, let's see if I can add 55 degrees. And I'm not going to use a trig function if I don't have to. I can say, like before, cos of 35 is equal to 4 over something. I could use the 55 now if you wanted to use that and say, oh, how about sine? Sine of 55 is 4 over c, but I like Pythagorean theorem, so I would just square both of these sides. I have no idea what 28 squared is. 0.28 squared plus my 4 squared, and then I got to take the square root of this mess. And I get the same thing. So you have a couple of different ways you can do this. There's not like a hard and fast rule, like you have to use this and then go in this order. It's just about what works and what doesn't work. You have a couple of examples on your worksheet here. So you can try those and then pull up the key. The key is pretty detailed to make sure that you kind of have that idea locked down, because there's not a whole lot of questions that are just solve me's for right triangle trig. Usually there's some kind of fake story that goes along with it. And the thing to remember, you're in a math class, right? You don't really care too much about the story. You care more about the triangle. It's a little geometry-esque, so you're going to want to think about drawing a picture. It does not need to be a good picture, right? You don't need to put windows on the hotel. You just need to have something to give you an idea of what's going on. So I got a straight trail from the hotel that's at an elevation, there's the word I'm looking for, feet. So this, imagine, is way up, here's sea level, and then I'm 8,000 feet above that. There's this scenic overlook that's 11,100 feet above sea level, right? But you're not going to walk up to the hotel, check in, walk back down, go over, and then go up 11,000 feet. There's this very convenient trail that goes from the hotel up to the scenic overlook here. for you to take your pictures. And what you want to do is figure out what's the grade of this. How steep is this trail? I don't know if you got any hikers or runners or anybody out there. And, you know, these things are very deceiving. What looks like to be a very small incline in like a car or when you're driving by, when you're running or biking up it, it's an absolute nightmare. That's why there's all these rules for like ramps for people who that aren't able to use the stairs, they need to be at a certain height, because if they're too tall, you can't get up them, motorized or not. So the distance from this level, from the hotel door to where the peak is not 11,100, but the difference between those two. So that's kind of a little catch there. Be on the lookout for tricks, because the math here is easy, right? You know Pythagorean theorem. You know how to plug stuff into your calculator to get angles for sine and cosine and tangent. It's going to be, are you plugging in the right number? So I have this length here. I have the length of the trail. So I have sine actually here. The sine of angle B is 3,100 over 14,100. And I'm just going to now have to talk about, well, what angle has that sine? And I'm going to need to go into my calculator. And it'll give you about 12.7-ish degrees. You round to wherever they tell you to round. 2 or 3 decimal places is pretty good. That's a pretty steep incline. I wouldn't want to have to run up it, but it's not terrible. The other one in the end of this PowerPoint is something that we don't talk about a whole lot. It's pretty interesting, and it will pop up a little tiny bit in Chapter 9, but it talks about, you know, are you northwest or southeast and those types of things. So let's see, I want to turn 90 degrees northwest. So if I'm this way, pointing north, and I want to turn west, that's how you read those. There won't be anything on the midterm or final about this. We don't do a whole lot of these types of questions with those types of directions. It's mostly just trees leaning against walls and such. Let's do a ladder question, because there's always a ladder question. Let's say you got a random ladder, a really big one, leaning against the wall. Let's say that it is 35 feet. And there's you got to get up to the roof. You got to clean the gutters, right? I'm moving. You got to check everything 4,000 times. So I got to get up here and check the gutters, and I know I got this ladder that's 35 feet. Maybe I know a little something about my house. I'm trying to think of a side length that kind of makes a little bit of sense. Let's go with 20 feet. How far away do I need to put this ladder? And what is the angle here, right? Because sometimes when you look at hard counts as far as distances, she goes, yeah, sure. I mean, I could put the ladder any way I want, any distance away. That doesn't mean that it's stable, right? If you put a ladder too far away, it's probably not going to stay up. And same thing if it's too close. I don't know if you ever try to climb up a ladder that's too close to what you're climbing next to, you're going to kind of fall backwards. So let's talk about what this angle is and then how far away is it. So what's the angle that the ladder makes with the ground? You can also talk about this as the angle of elevation from the ground to the top of the house. So the angle of this would be, oh, sine again, the opposite over the hypotenuse. So the sine of theta is 20 over 35, and I'm going to have to pause this to pull up my calculator. And that angle is 35 degrees. You probably wanted a little more like 45, so that's probably a little too short. Yeah, you probably need a shorter ladder for it to be a little bit more secure. If I want to know how far away to put it, right, because you're probably not going to say to somebody, hey, put that ladder in at a 35 degree-ish angle, right? You probably say, put it back X number of feet. Well, I got something squared plus 20 squared equal to 35 squared. I'm going to need to subtract that 20 squared from both sides. and then take a square root. Oh, looks like we may get something nice-ish. About, oh yeah, 28.7 feet, right? That's everything about this scenario is a bad idea, right? I should not be checking my gutters with this ladder. Ladder's too big. So that's the type of questions that you'll be looking at for right triangle trig.